Welcome. We're now going to have a run through of this worksheet, which you find in the link on Compass, Electromagnetism Worksheet 6B. It's the torque in a coil. It reminds us, firstly, of the formula that we're going to be using, which is BIA sine theta. So it's IAB on the NESA sheet. And also reminds us that theta is the angle between the area vector, which is the vector at right angles to the coil, and the magnetic field. So we often use an alpha, and alpha is the angle between the coil and the field, and then we say 90 minus that angle is theta. So let's have a look at going through these. This will be the first few questions here, and then I will let you go off, and I might be doing one of the harder ones later on. So question 1, a rectangular coil consisting of 5 loops measuring 10 by 20 centimetre and carrying a current of 10 amps is placed horizontally in a uniform magnetic field of strength 20 Tesla. What's the torque? So this is a standard question. So let's have a look at drawing this. I'm just going to draw it side on here. So there's my north and my south. I'm just being arbitrary with those. But more importantly, here, viewing side on, is the coil. The angle between the north and the south, so there's B, that's the direction of the magnetic field there. The angle between B's direction and the coil, alpha, is equal to 0. So alpha is the angle between this line and that line. That means that theta is 90 minus alpha, which is 90 degrees. So we now can use all the questions so this is question 1. So all the stuff from the question. So torque equals, I'm just going to use the one that I'm so used to using, which is NBIA, sine theta. You can use the one that NESA gives us, which is NIAB. Okay, sounds like a bank. N in the formula is, in the question is given as 5. B is 20 Tesla. I is 10 amps. And A is 10 centimetres by 20 centimetres, which is 0.1 times 0.2, which is 0.1 times 0.2. I always do it on a calculator just to make sure I don't get things stuffed up. 0.2. And that's meters squared. So that is times 0.02 meters squared times sine, in this case, 90. Now remember, we want the maximum torque when it's horizontal in the field. And that's what happens at 90 degrees. Oops, sideways. Okay. All we do now is place all those numbers in. So 5 times 20, times 10 times 0.02, times, I know sine 90 is actually 1, but I'm going to type it in anyway, and that's 20 Newton meters. Okay, so that's a straightforward run-of-the-mill question. Let's try question 2. Question 2 has a diagram with it. The diagram shows a single loop DC motor in a vertical position. Doesn't look very vertical, the loop is in the vertical position, I think it's trying to say, in a magnetic field of 5 Tesla. In its present position, there is no magnetic flux through the coil. Okay, so it is horizontal to the field. It's basically, that diagram just shows us that it is horizontal. It is just that it is up is this direction. Okay, so it looks vertical. If we're looking at side on. Okay. X and Y as this one over here. Identify the direction that that labelled wire will move when the power supply is turned on. So if we were using F equals BIL, so in other words, it is going to undergo the motor effect. The direction of this force will be at right angles to all to B and I. So we know that the current is going to flow out of the large one on our battery here. It's going to flow through this direction, so current is there. So I is flowing that direction through the coil. So we have B going this way, we have I going that way. Using our right hand push rule, our 3 fingers FBI rule, we put I going up, B going that way, so it's going to be pushed into the page. So F is into page. Okay, so if XY will be pushed into page, and this one over here on the outward journey where current is in the opposite direction will be pushed out of page. So we would get a torque on both sides of this coil. Okay, we're now asked to calculate the torque on the coil, the area of the coil. Okay, so when the power supply is on, the ammeter is 2.5 amps, the torque is 1 Newton meter, we've got to calculate the area. So we're just going to work backward. So question 2, we know that torque equals NBIA sine theta. We know that theta in this case is 90 degrees. I'm not going to go through that whole angle bit again. So it's horizontal to the field, so it's 90 degrees. It is a single loop, so N is 1. The torque is 1 Newton meter. B is 5 Tesla. I is, where is it? It's 2.5 amps, I think. Yes, it is. And multiplied by the area, and sine theta is 1. So sine 90 degrees, and we know that's 1. Okay, so area would simply be 1 over 5 times 2.5, just by cross multiplication there, and that would give us 1 over 5 times 2.5, which is 0.08 meters squared. Okay, moving on to question 3. Question 3, let's put the question up so we can see it first. A rectangular coil of 20 loops is positioned between the poles of a bar magnet and makes an angle of 30 degrees with the direction of the field. So you can see that this angle in here, that little angle there, that 30 degrees, is between the direction of the field and the plane of the coil. So that is an alpha. It is not a theta. So we know in this case that alpha is 30 degrees. Okay. If alpha is 30, theta is equal to 90 minus alpha, which is 60 degrees. So that's the quickest and easiest way to work each time. Just most of the time we are going to be talking about the angle between the plane of the coil and the angle of the direction of the magnetic field. Okay, so what else do we know? It's got 20 loops, and it's got 15 by 18 centimeters, this rectangular here, and the magnetic field is 5 Tesla, and the current is 2.5 amps. Okay, calculating the magnitude of the force on each wire, that would be this one over here. Calculating the magnitude of the force on a wire, that is the motor effect. So we'll be using F equals BIL sine theta. And in this case, sine theta is still going to be 90 degrees because looking side on, let's go over here. So this is A. Side on, that's the North Pole, and there's the South Pole. A and B are over top of each other, and it's that wire there. Okay, so the current is coming out of the page here. So there is, oops, I'll try and get that to sit straight up for you. Right, so the current is coming directly out of the page, and the magnetic field is this way. And that means that it's 90 degrees between the current and the field. Okay, so here's our trees in our forests. They're coming directly out of the ground, and it's north to south. So the force equals BIL sine theta. this case, it's 90 degrees. Now, that theta has nothing to do with the theta of the coil. It's a different formula, different theta, totally different things. So B, in this case, is 5 Tesla. The current is 2.5 amps. The length of AB is 15 centimeters, so 0.15, and we know that this is 90 degrees, so it's sine of 90. Oops, I'm moving off the thing. So it's sine of 90, and therefore I'm omitting it. Popping it in, we've got 5 times 2.5 times 0.15, and that would give us 1.875 newtons. Okay. Part B, it says calculate the torque. Torque equals NBIA sine theta, but this sine theta here is going to be the angle between the coil's normal and the magnetic field, which we discussed earlier, that alpha in this case is 30 degrees, therefore theta is 60 degrees. So the torque would be, there's 20 loops. B is 5, current is 2.5. The area is 15 times 18, so 0.18 times 0.15, and in this case it is sine of 60 degrees. Putting that into our calculator, let's move it around so I can see what I'm doing. That's 20 times 5 times 2.5 times 0.18 times 0.15 times sine of 60. It's 5.8. 5.8. We'll just round it down because everything else in this question is gone to 2 significant figures. So let's just round that one to 2 significant figures. So that is 5.8 Newton meters. Okay. Right, try question 4 by yourself and see how you go. If there's any problems, please email me. I'll come back with question 6 and 7. Okay, thank you.